Hello, and welcome to the Joy of Abstraction Book Club, Chapter 21. We've got all the way to Chapter 21, and I'm so excited. There are 29 questions, and this chapter is about it's about categories of categories. It's really kind of functors part 2, gathered into the idea of a totality of categories and related structures. So I'm really glad that so many people asked questions. I mean, of course, I don't know. Maybe it's just one person asking loads of questions. I think that there are at least several people asking questions because some of the questions have some overlap but aren't exactly the same. So let's jump right in. Luckily, the first few questions are quite straightforward, so I can warm up. I don't know how many breaks I'm going to need to take. I'm going to try and get the first 7 questions done before I take a break. Let's see what happens. First question, how would you pronounce? I can't read out this question. How would I pronounce the category that's denoted GPH? So with these categories, I'm really glad that you're asking. There's been a bunch of questions. I don't know if it's the same person who's been asking all along how to pronounce things, but I'm really glad you're asking because it's something that is difficult to know when you're reading a book. Whereas if you're at actual talks or lectures, then you can tell. So I would call that the category of graphs. If there isn't a sensible way to pronounce the abbreviation, then I would just describe it for what it is. So I might say the category of graphs, the category of posets, but for set, I would say set, because I can just say set, or mon or cat. But then the next question says, how would you pronounce cat when it's in all capitals to distinguish it from cat that's in small lowercase? So then I would say the category of small categories and the category of locally small categories. And then, is there a name for the is an element of symbol? Well, you know, I don't know. So I Googled it, and Google doesn't seem to think there is a name for it either. It's a bit like an elongated epsilon sign. I do remember teaching calculus one year where partway through the semester, I looked at a student's notes and found that they had written all of their is an element of signs as the number 3, because it looked a bit like an epsilon. And if you write an epsilon the wrong way around, you get a number 3. So that was a bit unfortunate. It's not a number 3. It's kind of elongated epsilon. So that's the first 3 questions. And now we'll move on to some more specific things, starting on page 309, the first page of this chapter. I'm having trouble understanding the last 2 sentences in the paragraph following things to think about 21.1. Right. So this is about functors, categories and functors forming a category. And the question says, why are we composing functions as opposed to functors on the objects and morphisms? Could you say more about the composition of functions? I'm wanting to hear more about the connection between functors and functions. So the first thing we can do is type check ourselves. So you can only have a functor if it goes between some categories. And if it's not going between categories, but it's going between sets or collections, then it's a function. And so that's what's really going on here. So let me share that whiteboard screen for a second. So this is about the identity functor. And so the point is that if you've got a functor, that's a functor between categories. It's a functor because it's going between categories. But what is a functor? Well, remember that the definition of a functor says that we're going to act on objects and we're going to act on morphisms. And there's actually a question later on that says, what does action mean? Maybe I'll just jump to that question for a second. There was a question that said, what do you mean by action? Right, it doesn't mean action, it just means a function. We can say that a function sends elements over here to elements over there, but we can also call that the action of the function. And we can also talk about the action of the functor because it sends objects to objects and it sends morphisms to morphisms. So a functor between categories, it's a function on objects. So when you isolate it, wow, this thing is not very responsive today. I'll just have to write more slowly. So it's a function on objects because we've got a set or a collection of objects for C, when we isolate our attention on the objects, it's just a function. And then it's for every pair of objects, X and Y in C, a function. Because now we're acting on Hom sets. So again, that's a function that's going from the Hom set from X. That's the set of arrows from X to Y, to the set of or collection of arrows from F of X to F of Y. So we also have axioms for functoriality. But what this is telling us is that fundamentally a functor consists of a bunch of functions in different places. And that's because fundamentally a category has different levels of set. So because a category has a set of objects and a collection of morphisms, let's say, then there's going to be a function on the objects and a function on the morphisms. And so when we're looking at the identity functor, which goes from a category to itself, the action on objects, it's the identity function on the set of objects. And then on morphisms, we say for all X and Y in the objects of C, it's going to go from C, X, Y. Now, here we went to D of F of X, F of Y. But D in this case is also C. And F of X is the identity function acting on X, which just leaves X the same. And then again, it leaves Y the same. So we're going from the same set to itself. So it type checks for us to use the identity function there as well. And does that deal with that question? Could you say more about composition of functions? So composition of functions, I think, was in the chapter on sets and functions in the interlude. Let's see, was it? Was it? Yes, it was on page 143. So when you compose functions, you do the action of one function, and then you do the action of the function after it. So composition of functions, if you're going from a set X to a set Y to a set Z, and these are functions, then you start with an element X, and the element X gets sent by the action of F to F of X, right? And then that element gets sent to G of F of X. So what I said in the original chapter was it's like you have this one machine where you have inputs and outputs, and you have this other machine where you have inputs and outputs. And the composition says whatever you feed in here pops out an output that you immediately feed in here, and then it pops out an output. Okay. So hopefully that's dealt with that question. Okay, so the next two questions. The next couple of questions are about the relationship between monoids and categories. I feel like there were some more questions about that later. Yeah, there were, but it comes up in a couple of places. But maybe I'll deal with all the questions about monoids and categories together. So, am I right to have the impression that there is a special relation between monoids as such and as totalities and categories in general? Yes, I think that's come up before. So we originally said we could define monoids to be one object categories. Now, I will say that this is a very profound relationship that has been the subject of quite a lot of my recent research. So it's right that you should feel that there's some stuff going on that isn't being said, because we say a monoid is a one object category, but this is very problematic. So as category theorists, we shouldn't be talking about individual things, but we should look at their totalities. And so if you take the category of monoids and monoid homomorphisms, you can look at the category of one object categories, which are called degenerate. So I will call those degenerate categories. And that's the categories with only one object. And the thing is that there are a lot of different things that you could pick to be that one object. So for example, if I take the monoid of natural numbers and I want to express that as a category with a single object, what's that single object going to be? So this is related to the next question, which says, could you please clarify what's meant by the dimension shift and the need to fabricate a single object from somewhere? And so the point is, in this dimension shift is that a monoid only has objects. Well, I'll call them elements. The elements have a multiplication on them. Whereas a category with only one object has morphisms and a one object. And then it's got composition of morphisms. So the elements of the monoid, the objects of the monoid, correspond to the morphisms over here. And that's where the dimension shift is, because this is the 0th dimension and that's the first dimension, whereas this is the 0th dimension over here. And so the 0th dimension in the monoid is corresponding to the first dimension of the degenerate category. And so the thing is that it doesn't really matter what that single object is, but you do have to say what it is. And so that single object could be an asterisk, or it could be the letter A, or it could be an elephant. And so you have to say what that one object is. Now, it doesn't make any moral difference what it is, but it does mean that these categories are not exactly the same. What it really means is they're not isomorphic, but they're equivalent, because if you took a whole load of degenerate, there could be loads of different degenerate categories who all represent the monoid of natural numbers, but they could have increasingly ludicrous things as their single object. When you go back to the left, you forget what the single object is, so they will all become the same thing again. And so they are all canonically isomorphic over here, but that means that this is not an isomorphism of categories. And so monoids and degenerate categories aren't exactly the same. You have to perform this slight shift. Then the things get worse when we try to think about coproducts. So then I'm going to skip ahead because now we're talking about these things. There are some questions about the coproducts of monoids. And so someone said, I think I'm missing something in T21.9. So T21.9 says, see if you can understand why coproducts of monoids are not the same as coproducts of one object categories. There are two flavors of answer to this question, the idea and the formalism. And so there's another type of answer to this, which is the way that we use language when we're doing category theory. So if I say the coproduct of monoids, what I mean is the coproduct inside the category of monoids. And if I say the coproduct of one object categories, what I mean is that their coproduct as categories, and those aren't necessarily the same thing. So you can't, it's a bit sloppy, I admit, as the way language goes, but that's how we understand it. So you can't just abstractly take the coproduct of two things if you don't know what category you're working in, because they can come out to be different depending on what category you're in. And so the point here is that there's a category of monoids, and that can map into the category of categories. And if we chose what the single object is always going to be, then we can ask ourselves about the coproduct of some things as monoids. So if this is sometimes called sigma because it's a suspension, because we're adding an object and taking everything up a dimension. So the point is, if we have monoids A and B, we can take their coproduct as monoids and then take the suspension of it. Now, by definition, that is definitely going to have a single object. Or we could take the suspension of A and coproduct it with the suspension of B as categories. And this version, perhaps I'll change color for a second. This one has one object. by definition, because sigma always just adds a single object. Whereas this one has two objects and it's disconnected. Because when you take the coproduct of categories, you just have this one category over here and this other category over here. So you'll have a single object category over here, and you'll have a single object category over here, and you put them together in a category like this. So you've got two objects. So then somebody else asked, related to this, have I understood correctly that the functor from monoids to categories does not preserve coproducts while it does preserve products? What should we make of this asymmetry? So yes, that is what this is saying. This functor does not preserve coproducts. And usually when something doesn't, so there's several questions about some further abstraction in this chapter, and it's usually to do with adjunctions. And so adjunctions are something that we don't get to in this book, but an adjunction is a relationship between a pair of functors, but it is very directional. So there's a left adjoint and a right adjoint, and it's a weakening of the concept of an equivalence. So in equivalence of categories says that you've got a functor going this way and a functor going that way, functor going back again. Equivalence of categories says that GF, one is isomorphic to GF, and FG is isomorphic to 1. And then we can try and get this, there's a reason I've written it this way around. So GF says do F first and then G after. So this is the identity on C, and this is the identity on D. And we'll get to that, I think, in the next chapter. This is the weakened version of sameness for categories. An adjunction weakens it even further and says that there's a natural transformation from the identity to GF and a natural transformation from FG to the identity and axioms. So it is a relationship between these things, but it's weaker and it has asymmetry in it. And so in this situation, F is called the left adjoint to G, and there's always asymmetry that arises when you have this kind of situation. So I don't want to do an entire lecture about adjunctions. So I'll just say this, that one of the things that's true about adjunctions is that if you have a left adjoint, then you preserve limits. And if you have a right adjoint, you preserve co-limits. So that's where a lot of asymmetry often comes from. And how much more shall I say? So that was an if in a particular direction. Then there are theorems saying that if you're in a nice situation, then the converse is also true. So that just preserving limits or co-limits is a sign of being part of an adjunction. Now, we're only talking about products and co-products here. And there's definitely an asymmetry going on, but it's kind of worse than that, because what's actually going on is that if we go back to this situation up here, you might say, is there an adjoint here? And the thing is, if you just take an arbitrary category, then you can't really go back to a monoid because it's got more than one object. But what you can do is, given any object, you can produce the monoid of morphisms on that particular object. And so what that is saying is that rather than going from cat, we're going from sort of pointed categories. And this is analogous to the concept of a pointed topological space or a pointed set. So a pointed set is a set with a chosen element. I talked about this a bit in the last video, where you specify an element that's kind of special. So this is quite important in topology, because if you're looking at loops in a space, you want to know where your loops are start and finish at. And so you often have to start with a chosen base point in your space in order to make anything sensible happen with your loops. So you can do that with a category as well. And I'll call that cat with a point. So that just means a chosen object. So now we can send any monoid to a category with a chosen object. And given a category with a chosen object, we can produce the monoid of morphisms at that point. And now the thing about adjunctions is if F is left adjoint to G, then the morphisms from f of x to y are isomorphic to the set of morphisms from x to g of y. And so we might call this sigma for suspension, and omega is quite a typical symbol used for loops. And if we look at this, what we're saying is that, okay, look, if I turn a monoid into a one-object category, and I think about the functors from that one object category to, I should have thought about this harder to get the size right. So I'm thinking about functors from that one object category into another category, but it's got to preserve the base point. And so what I do is I map the single object to the chosen base point, and then I'm going to have a monoid map from that monoid to the monoid at that point. And so what this is saying, I think, if I did it right, is that functors from sigma of a monoid to a category are basically the same as monoid maps from the original monoid to the monoid of loops in there. And so I'm going to stop and check that I did this the right way around in a minute. So this is indicating that there's an adjunction like that. So sigma has a right adjoint, so we would expect that to preserve coproducts. And so the point is that in the category with a base point in the category of categories with a base point, when you take the coproduct of them, you don't just take their disjoint union, because now what's the base point going to be? You have to take the disjoint union and stick the base points together. So it's just like in the fact that if you take the category of pointed sets, the coproduct of pointed sets is not the disjoint union of the two sets. It's the disjoint union where you have to glue the base points together, because otherwise, well, you'll have too many base points. So now in the category of pointed categories, the coproduct, the coproducts will be the same as the coproduct of monoids, but this is not the same as the coproduct in categories. So if we take categories without a base point, here's the thing: you can freely add a base point to a category, and you can forget that the categories with a base point you can forget, but the free functor is left adjoint to the forgetful one. And so now this is often the case that there's a free functor and a forgetful functor. And now see what's happened is that we've got functors. We've got adjoints going in the wrong direction. So if you try to compose a left adjoint with a right adjoint, things tend to go wrong. And here we're composing a left adjoint with a right adjoint. And so although we preserved coproducts up to here, we're not going to preserve coproducts up to here anymore. So this is all really profound, and I should have prefaced it with all sorts of things saying that if you're not supposed to know about adjunctions, but someone asked, and so I thought I would provide a little bit of explanation. I will now stop and check that I got my adjunctions the right way around, because on a video or by a blackboard, you never know. So let me just pause. I looked that up and found that I did get the adjunction the right way around, but then I found that I shouldn't call that category the pointed categories. I shouldn't probably call them pointed categories, because apparently pointed category means something else. So just be aware of that. I also realized I haven't really addressed the question of the asymmetry. So this situation makes it look like the functor from monoids to categories definitely shouldn't preserve coproducts, but it also doesn't show why it would preserve products. And the best answer I can come up with for that so far is that it's to do with this abstract stuff that keeps coming up and that I keep putting in footnotes, and then there keep being questions about it. So it's to do with the fact that monoids and categories are both categories of algebras for monads. And when you make categories of algebras for monads, products tend to work better than coproducts, or they're easier anyway. And that's basically, I think that's what's going on here. It's not a very satisfactory answer, and I haven't quite got to the bottom of why it's true, but I think it's to do with the fact that if you take the underlying data for a monoid, it's a set. And if you try and do this on underlying data instead of the algebraic structures, you're on sets over here and you're on graphs over here. And there is a functor there which sends, there's a functor there that sends a set X to a degenerate set, a degenerate graph where the set of objects is just terminal. You can start with a graph and send it to its set of morphisms. And you can't do that if you start with a category. You can't send it to its morphisms and expect that to be a monoid, because it won't be one object anymore. But with this, before you've put the algebra structure in, you can do that. And there's an adjunction there. And if I've got this the right way round, it's a left adjoint. So this one preserves products, because if you take a product of a pair of sets here, and then you send them over there and you take their product here as graphs, you will get the product here and the product of 1 cross 1 here. So it will be the product will map to the product. And so then if you construct monoids as algebras over here, the products work fine. And if you construct categories as algebras over here, the products also work fine. And so the whole thing with products is fine. So that is all way beyond the scope of what this is about. So I said that rather briefly, but I will move on now. Let me just mark off the fact that I've addressed those questions. Okay, next question. Page 311, okay, so questions about graphs. When we're thinking about the underlying data for the category as a graph, is that graph a category itself? No, it's a graph. So the underlying data is a category without the algebraic structure. So it is not a category. It's just a pair of sets and a pair of morphisms between them. Could you please say more about the difference between extra structure and the underlying data? So the underlying data is just sets, and the extra structure is algebraic information. So that algebraic information is where you can take some things, combine them, and to produce something else. That's what structure is about. And then there's a related question that says, in the category of graphs, are the morphisms functors? No, because the objects aren't categories. You can only have functors between categories. If you're in the category of graphs, that's just a diagram of sets and functions. So the morphisms can't be functors because we don't have categories. And then there was another question I sort of missed, which says, with respect to the sentence, however, a category is not just a set with extra structure because its underlying data has objects and morphisms. Could you please say more about the difference between extra structure and the underlying data? Right, so it's not just, a category isn't just a set on which you can do stuff, right? So a set with extra structure is a set where you can have some way of combining the objects of the set together. Whereas a category has objects and morphisms. And so it's got a set of objects and a set of morphisms. And it's only once you've got all of that data can you start combining things. So the how you get to compose things is not data because it's a process. And so that's why it counts as extra structure. More technically, it's because this is the underlying object. If you express categories as algebras for a monad, that's the underlying objects. And then the monad is the thing that puts the algebraic structure on it. Okay, page 313. Near the top, you say, in good situations, the free and forgetful functors are in a special relationship called an adjunction. Can you give an example of a bad situation where the free and forgetful functors are not adjoint? That's a good question. Let me check my wording, because usually I'd only want to call something a free and forgetful functor if it is in an adjunction. I think I'm hard-pressed to think of a situation, so I bet I can come up with something. Let me pause for a second. No, I think maybe that's slightly suspect wording, because there isn't a technical definition of a free functor and a forgetful functor. They're really informal terms, and the only way I can think of to make them formal is to say that there's an adjunction. So I think what I mean is not that in good situations the free and forgetful functors are in a special relationship called an adjunction. I think what I mean is in good situations there is an adjunction between, and we can call it a free and forgetful functor. Okay. Okay, so it's another of these abstract footnotes next, and it's the same answer as always. Page 314, can you elaborate on how the initial terminal category follow from general theorems about functors? Wait, is that what the footnote actually says? Oh, it's how you construct initial and terminal categories. So the point is that terminal objects are limits and initial objects are co-limits. And if you have a left adjoint, you preserve limits, and so you will preserve the terminal object. And so, okay, so the point is that there's an adjunction, there's the category of graphs. So I put this in footnotes because it was too much to explain for the scope of the book. So now that the question has been asked, this is too much to explain for the scope of just reading the book. But since it has been asked, I will just quickly say that there's a free and forgetful adjunction from graphs to categories. So we could call that free and this the forgetful one. So U has a left adjoint, so it preserves limits, including the terminal object. And I have duly drawn the adjunction with two arrows going the same way. Okay, good. And so what this is telling us is that if cat has a terminal object, which it does because it's a category of algebras, so there's always a terminal object, then when you take its underlying graph, that still has to be the terminal object here. So we know that the underlying graph of the terminal category has to be the terminal graph. Then on the other side, F preserves co-limits, including the initial object. So that means that the initial object has to be the free category on the initial graph, and the initial graph is empty, and the free category on the empty graph is empty. So that's how we know that. Okay, that's that question. Next question, I'm wondering how compositionality works with the empty functor. The empty functor would be like the empty function because there's nothing to map. Right, so if E is the empty functor and it has to compose, what would F, E, G look like if F and G are functors? So it's also the initial, it's the unique thing from the initial object, right? So if we just look at the initial object, so what we're saying is that we've got the unique map from the initial object or the empty category to another category. Now, if we're trying to compose something onto the beginning of it, there is no functor here unless it's already from the empty category itself. So that's not very interesting. And then if we compose after it, well, then we have to just get the unique map from the empty thing as well. So all we're ever going to get is the unique functor from the empty category that does nothing. So then there are some questions about product categories. By product category, I just mean category that is a product. So that if you take categories C and D and you construct their product, that's a product category because it's the product of these two categories. And then the projection functors are the projections. And so I think that deals with those two questions. And then someone said, are projection functors forgetful functors? I mean, yes, because they forget one component. If you're projecting from C cross D to C, you are forgetting the D component. But I would hesitate to call that a forgetful functor because forgetful functors, it's almost forgetting too much. That's why I would call it a projection. I think I wouldn't say it's not. Do you know what I mean? I wouldn't say it's not a forgetful functor, but also I wouldn't just call it a forgetful functor. It's a projection. I think that there is yet another question about a footnote. So at the bottom of page 315, it's talking about how the proof that we just proved that how we just worked out what products of categories are, and we noticed that that proof is very similar to the proof of products of posets and products of monoids. And that similarity is a sign that something is going on, and that's the thing that's to do with it all being algebras for monads. And so it's not about why poset to cat preserved products, although it's probably related because poset is also a category of algebras. And basically, whenever you are a category of algebras for a monad, limits are pretty easy and well behaved, and co-limits are okay, but limits are much easier. And so the stuff with limits tends to go better than the stuff with co-limits. That is what that is about. But in order to understand it, or in order for me to explain it, it requires a lot of stuff about monads and algebras, and I think that's too much for now. I think I have dealt with the next question, which says, what do you mean by action? Right. I just mean what a function or a functor does. And then we're moving on to some different things. So I think I'm going to take a little break. Back in a moment. Okay, I've had coffee, I've had chocolate, raring to go. Page 318, it's mentioned that the cube category is the product of the product category I cross I cross I, but according to the definition of product category, I thought that the latter has just one morphism. And someone else says, a more abstract approach is to observe that this cube is a product of 3 copies of the quintessential arrow category, one for each distinct prime. How does the cube get built up? Okay, so let's look at this, and let's do this just the product of 2 copies of I first. So if I, as it were, write I to be the quintessential arrow category, and I'm going to call it 0 to 1, and there's just one morphism F, okay? Now, it might look like I cross I only has one morphism because there's only one morphism, but don't forget, there's the identity on 0 and the identity on 1. So I cross I has as objects 0, 0, 0, 1, 1, 0, and 1, 1. And then there are morphisms like this. So there's F, the identity, and there's the identity, F. And then here, there's F, the identity, and there's the identity, F. And we don't have to draw this one up here, but this one up here is F, F. And so if you then do I cross I cross I, then you get the cube, because what you get is, I won't draw the brackets because it's really boring. You get 0, 0, 0 at the bottom, and then you get 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. And there's only one possible morphism. So this one goes F1, 1. Right, this one goes 1, F1. And this one, I don't even know if I'm doing it the same way up now that I think about it. Perhaps I'm doing it the other way up. I seem to be going from bottom to top here, but it doesn't make any difference because it's a dual. Then this one is 1, F1. And this one is 1, 1, F. And this one is F1, 1. So just in one component, something's going from 0 to 1, and that's where there's an F. So then here, the one component is the last one. So it's 1, 1, F. And then this one is 1, F1. It's quite possible I made a mistake here. Let's see, 1, F1, 1, F1. I'm missing that one, which is F1, 1. And so you see the parallel ones have the F in the same component. So this one will be 1, 1, F. This one will be 1, F1. And that one will be 1, 1, F. And so if you wanted to, you could write the 3 copies of I differently. So instead of calling them all 0 to 1, you could call them non-white people to white people, non-male people to male people, non-rich people to rich people, and so on. But structurally, in terms of this category, it doesn't make any difference what you call them. It still produces this cube. So then we have a question, page 320. Why is the upside down version of the left-hand box not isomorphic to the left-hand box? So this is about the diagram where I said this category is not isomorphic to this one. And what I say is there's no isomorphism between the categories pointing in these directions, and that this is not a rigorous statement. And so can you interpret it rigorously and prove it? And so obviously those 2 categories are isomorphic because they are the same category. So obviously that's not what I'm trying to say. I shouldn't say obviously because this question shows it's not obvious, but that isn't what I'm trying to say. So as I say right below it, the rigorous statement is that the bijection on objects shown in this way cannot be extended to an isomorphism of categories. So if you try and make a bijection on objects like this, then that will not be an isomorphism of categories because it won't even be a functor, because there is no way to map this morphism to a morphism from women to men because there isn't one. And so it's not even just that it's not an isomorphism of categories. There isn't even a functor in which men get sent to women and women get sent to men. So why is the direction of the arrow of the rightmost box as so? It's because I'm making a point. And I'm making a point that if you have an arrow going the other way up, you can't make a functor from there to there. So that's why that's the answer to that question. So the next questions are about the definition of functor and the blackboard bold face for the categories, as opposed to the calligraphic face. So this is on page 323. So in the first part of this discussion, I'm talking about the possibility of having a bijection on objects and a bijection on arrows. And because I'm talking about total sets of arrows implicitly, that's why I started using blackboard boldface, so that I can think about a total set of arrows. But in the definition of full and faithful, I never talk about the complete collection of the total collection of morphisms. And so that's why I reverted to the calligraphic letters, because it works perfectly fine even if you're only locally small, because you're only ever thinking about individual hom sets. In fact, in some sense, the definitions of injective and surjective work perfectly fine if you're only on collections and not sets. So it's possible that it makes no difference anyway. Last 4 questions. Page 324. The second example. Oh, yes. So this caused a little bit of consternation, which is the attempt to make full and faithful functors from this category. So there's the, I don't need that to be read. There's this category, which has completely unrelated objects. And then it ends up going to a category that's only got a pair of objects. And either it has 2 morphisms or 1 between them. So whether it's got 2 morphisms or 1, we're kind of doomed, because if we try and send A and A prime to the same object, you're ending up sending them somewhere where they are isomorphic, where they didn't start off isomorphic. And so in order to make sense of that, we will need to, these things will need to be isomorphic. And so I feel like there's a diagram of this somewhere. Yes, it's like the diagram on page 322. So in the diagram on page 322, what we have is an isomorphism here and an isomorphism here. And as a result, there's an extra morphism from A to B primed, which is like the same one as the morphism from A to B via this isomorphism. And there's an extra one here as well. And so now, if we if we send that over here, this is now full and faithful. Because if we restrict to a pair of objects, we will always get ourselves an isomorphism of composite. So if we restrict to A and B primed, then they map to D to E, and there's a morphism from D to E, but there is also a morphism from A to B prime. So someone said, will we always have the same crosswise element problem? And the answer is yes. So if we wanted to map to a place with two morphisms over here, we would have to have two morphisms everywhere here as well. On page 327, in the paragraph beginning, it is crucial to note that. Can you please explain the elements that are being used? Page 327. It is crucial to note that the definition of pointwise equivalence is a weakened version of bijection, not a higher dimensional version of isomorphism. It uses elements all over the place and so is not categorical. So the definition of pointwise equivalence says that we're essentially surjective on objects and locally full and faithful. And so it says for all D objects of D, there exists a C in the objects of C such that F of C is isomorphic to D. So that's the definition of essentially surjective on objects. And look how many times it's used an elements thing. Look, this says is an element of, that says is an element of, and this, but that doesn't say it is an element of. So the point is that if we were trying to make this categorical, this should work for any inside any two category. So we shouldn't be thinking about elements of C or elements of D, because these are just objects. C and D are just things, and this is just an arrow. We don't know that C has objects, and so that's where we've used some elements, because we're kind of using the fact that C has objects. So we could not immediately place it in other categories, means that in an arbitrary category, if we were just in some arbitrary category with objects and morphisms, this thing doesn't make any sense. We don't know that we've used some special property about C in this case, that it's got objects. In general, it might not. So what if these were just points in a space, right? This could be a point in a space, and that could be another point in a space, and this could be a path between points in a space. Then it doesn't make any sense to say for all D elements of this point in a space. So that's what it means by not being categorical. And the last question, page 327. In the proof of proposition 21.7, it starts with, suppose we have an isomorphism. So, but what if we have no isomorphism? Does that mean the proof will only apply to categories with isomorphic objects? So first of all, every category has isomorphisms because it's got identities. And so there are always isomorphisms. But 21.7, so it says, suppose, this proposition says, suppose that F is full and faithful, then F is essentially surjective. So what we're doing is we are supposing that F is full and faithful, and we are trying to show that it is essentially injective. And the definition of essentially surjective says, for all C and C, if there is an isomorphism there, then there is an isomorphism here. And so in order to prove that this is true, we have to suppose that we have an isomorphism and then deduce something. So it doesn't matter whether or not we have an isomorphism, although we do because there are always identities. It just is saying whenever we have an isomorphism, something else is true. So this doesn't mean that it only holds in categories with isomorphisms. It's the premise of the thing we're trying to prove that says whenever we have one of these things. So if I'm trying to prove something that says whenever I have an elephant, then the elephant has a trunk, then it doesn't matter whether or not I have an elephant. It's still true, right? Because it's only saying that whenever I have an elephant, it has a trunk. And so that's quite an important thing logic to understand about proofs. If you're trying to prove that whenever X is true, Y is true, you're not saying X is true. You're just saying that whenever X is true, something has to follow from it. And that is all the questions. So finally, some praise and joy. I really appreciate you writing such an enlightening book for beginners. Thank you. Congratulations for the Babbage interview. It was delightful. Thank you. Thank you for being our guide on this journey to category theory. Thanks for your patience. Thanks for writing the clearest category text I've ever encountered. Thank you for your dedication. Thank you, Eugenia. Thank you, Topos Institute. Thank you, anonymous classmates. And this one, which I really appreciate. Thank you so much, Eugenia and the Topos Institute. This has been such a golden opportunity. I've been putting a lot of time in, and then you're putting a lot of time in, and it's a wonderful cycle of motivation. And so I suppose I'll stop the share now so that I can end with a bigger picture. And now I can freak out about whether I'm still recording, which I am. So I'm really glad that this has been a good cycle of motivation. It does seem that there are many questions and that people are really engaged with this material, and we've got all the way to chapter 21. And are there 24 chapters? Let's see. I think there are only 3 questions left. So there's natural transformations, the Yaneda lemma, and higher dimensions. I'm going to tell you right now that if someone asked me to prove the Yaneda lemma, I'm probably not going to do it in a video. There are plenty of proofs out there. So I apologize in advance for that. But thank you to everyone at the Topos Institute for helping us with this. Thank you for asking questions. And also thank you for just watching, even if you're not asking questions. This is an amazing journey, and I'm glad you're here. And I'll see you next time. Bye.